kicked off. This is our third time. Yeah, third time. So this particular plenary session is sort of the brainchild of doing something in an integrated fashion with the Society of Petroleum Engineers. And this makes the third year now that we've held this plenary. It's been very successful the previous 2 years, and I'm sure it will be this time as well, given the speakers that we have. The idea behind this plenary is to bring a technical issue into the conference in a way that is typically, at least historically, has not been brought into the conference. So addressing things from an engineering and geotechnical perspective rather than purely economic perspective. So, with that said, we actually have two speakers today who will address something that is very near and dear to a lot of people who have been tracking the shale revolution, as it's been called, and that's the topic of today, is water development. So we're first going to hear from Meagan Mauter. She's a professor at Carnegie Mellon University, and I'm going to skip in the interest of time long introductions. But then after Meagan speaks, we will move immediately to John Walsh. And actually, before both of them, I'm going to give the mic to Bill Furlow for a minute, because he's been instrumental in helping me to put together these sessions. He's the liaison, if you will, to the SPE from the USAEE side. But after they've spoken, so I want to hold questions until the end. Again, this is just in the interest of time. After they've spoken, we'll have time to entertain questions, and I've been told by both that you are free to ask anything in the domain of what they discuss, even if it's not specific to something they bring up in their presentation. So, Bill.
Just real briefly, my name is Bill Furlow. I do business development for Society of Petroleum Engineers. And what that means for SPE is different than general business development. I develop technical content. As Ken said, we've done this, but this will be our third year together, and we always have really good results with these sessions. One of the key things, though, is what he mentioned, the interaction with the audience, and to make sure that you get to ask your questions. And John Walsh is 30 years in the industry. I would say he's pretty much SPE's go-to water guy. So in the area of produced water and water handling, he's about as good as they get. So you have a real opportunity here to ask any and all water-related questions. I think everyone on the table would agree that water it's currently a very important issue, and it's going to be the coming issue. It's just going to get more and more critical going forward. So this is, as always, Ken's picked a really timely topic for the session. So thank you for inviting us. We appreciate it.
Now I'll invite Meagan up to the podium. I'm going to be advancing her slides, so when she comes to me in the head, I need to sort of advance the slides. But Meagan is actually with the School of Engineering and Policy at Carnegie Mellon, so she sits in a very sort of unique domain. Yeah. Is it possible for everybody over here to slide over? Because I think she's going to just walk in front.
Is that a problem for... I think it's going to be a lot easier if I can talk to this one. Okay, so thank you so much for your flexibility here. For me, it's always helpful to have the laser pointer in hand. Thank you, Ken, for your kind introduction. As Ken mentioned, I'm a faculty member in two departments. One is in the Department of Engineering and Public Policy, where I think about sort of the policy context for technical innovation. The other is in the Department of Civil and Environmental Engineering. I also have appointments in chemical engineering and material science, where I do a lot of work on innovation in new technologies, particularly to treat high salinity wastewater. And high salinity wastewater is a particular issue at well sites. I'm not going to go into tremendous detail today about the work that we've done on using low temperature heat to drive separations. I'm not going to talk about the material science behind membranes, because I have a feeling that no one here cares. But I am going to try to talk broadly about the context for our work and some of the research opportunities that I see, particularly for economists and people with econometrics backgrounds, to look at critical issues in produced water management, and especially to think about those issues in the context of the Marcellus play. So the title for, well, sure, this is fine. It's okay, the timing is going to be an adventure. But I just wanted to give a brief introduction to those of you in the audience who may not be familiar with water use in drilling and production in shale plays. And I'll say that there are three kind of critical takeaways from understanding water use. The first is that water-related costs in shale gas development is actually very high. You need to pay for water acquisition. You also need to pay for water disposal. The second is that we do use a large volume of water. Usually it's about 5 million gallons per well in the Marcellus. It's a good rule of thumb, although that really depends on the length of your lateral more than anything else. But I will say that it's a large volume of water used in a very short amount of time. And so that puts stressors on the system that wouldn't otherwise be there, both from a water supply perspective, as well as the challenge of designing and maintaining infrastructure that doesn't need to be around for very long and experiences variable flow rates and variable feed water qualities. The third is that because there are many different stages in water management at the well site, there are a number of different risk pathways. And so as we think about managing risks associated with water on shale plays, it's really important to dissect that and to look at all these potential interventions. So I just want to give you kind of a timeline of what happens. We have some site preparation that goes on for a couple of weeks, drilling over a couple of weeks. You're going to acquire water and start fracturing, probably over the period of a couple of months, although that's shortening dramatically over the past couple of years. If you can advance a couple more, Ken. I don't have any other animations, so we should be okay. You have a flowback water comes in the first pulse. This is a lower salinity flowback. And then you're going to get produced water, which is more characteristic of the water that's actually in the play itself, coming up or being produced. And that's likely to happen over the entire duration of production, although the volumes decline over time. If you can, one more, this is kind of a picture of a site in Pennsylvania, and I'll just point out that often there is a impoundment here to store water during this water acquisition period. Typically the wastewater is stored on tanks on site at this point, and you'll see that there's both gas pipelines as well as roads that are being built to help manage these waters. Okay, next slide please. So because there are many different stages in water acquisition, water treatment, water disposal, it kind of opens up a number of opportunities for risks. My colleague, Mitch Small, ran a very nice NRC committee on risk management and governance issues in shale gas development. I was a part of that a couple of years ago, and we published a paper that highlight the principal risk domains in water. There are risks associated with source drawdown, so that's a lot of consumption of fresh water. There's certainly some risks to groundwater associated with poorly drilled or cased wells. I would say too that a lot of attention has not been paid to how to manage that wastewater once it comes to the surface. And in terms of the size of the risk, I think that it's this wastewater in the Marcellus that poses the largest risk. I'll also say that what's really important to understand is that water in isolation is a risk domain, but water also has a lot of instances where there's kind of synergistic risks with these other risk attributes. So there's a strong connection between water and air quality, both from the perspective of maintaining wastewater in closed containers instead of venting the dissolved organics directly to the atmosphere. Also in treating and managing water, there's a lot of energy consumption, and so it is important to think holistically about the risks associated with water management. Next slide, please. Okay, so a lot of work has been done on risks. I think that the focus in water has primarily been on local risks. I like to take a step back in my own work and focus more on what the regional risks are. Water is a very regional entity, and so the rest of my talk today is going to focus primarily on that regional component. Next slide, please. To that end, my colleagues and I also published a paper at ESMT a couple of years ago that highlighted some of the regional variation in water-related impacts of shale gas development and what some of the implications are for emerging shale gas plays, not only in Pennsylvania, but also in Argentina, the Vaca Muerta, in Australia, and in China. The point being is that the context for water resources is very different from play to play, and so the risks and emerging issues, the stressors that water and shale interact to produce look very, very different. So I'll emphasize today that I'm going to focus mostly on the Marcellus in my analysis, where the issues are not so much with water availability. When you're pulling from a very small stream, that can pose limits to your rate of water withdrawals. But the biggest issues here in the Marcellus are wastewater disposal. We do not have a large number of Class 2 injection wells. There are about 6 or 7 in the state. And I would contrast that with Texas, which has something like 35,000. And the importance of managing water so that you can reuse water in your operations becomes particularly important here in the Marcellus. Next slide, please. Okay, so I'm going to kind of focus on I'm going to describe 3 analyses that we've done that help us responsibly meet water demand or water treatment demand in shale gas plays. The first kind of approach that I'm going to push is that it's really important to understand the system drivers of water management at the play level. I'm going to talk about some work we've done to optimize the water management process, as well as the treatment process, and then I'm going to do a review of PA Act 13, a very quick review of PA Act 13 and some of the implications that has when thinking about jurisdictional equity in terms of damage compensation. Next slide, please. Okay, so I think I mentioned that we have very, very few Class 2 injection wells, so disposing of wastewater is a challenge in the region. One of the ways that operators have historically done this or dealt with that issue is to dispose of water either by transporting it to deep well injection facilities out of state, particularly in Ohio. The other option is to increase the amount of water that you're reusing in subsequent hydraulic fracturing operations. So the extent to which you can reuse certainly bumps down the amount of trucking or transport that needs to happen. What we've done is look at all of the wells and the disposal facilities that were drilled and used in 2011. 2011 is an interesting year because that was the year that Pennsylvania worked with shale gas operators to put in place a voluntary agreement not to discharge these high salinity flowback waters to wastewater treatment facilities. And so companies had to suddenly look for new methods of disposal, and we have kind of an interesting take on how companies have adapted to that new regulation by looking in 2011. Most of the draft policies were put in place in 2010, but April 2011 is when this actually came into play. If you could, just one more thing here, I want to say that we looked at where the wells were drilled, we looked at where the waste was disposed, and we were able to sort of estimate, using shortest distance methodologies, where truck traffic to transport this wastewater would have occurred. So there was a significant amount of mileage driven along this I-80 corridor, also in the I-76, 376 area. Next slide, please. Okay, so if you sum up all of that mileage driven, your average transport distance one way for water, both flowback and produced water in the Marcellus in 2011 was 113 miles in one direction. Usually these trucks are coming back the other direction, typically empty, and so you can kind of get a sense of what sounds like a lot of truck transport. I'll say that this is about 0.1% of traffic in the state of Pennsylvania. It is not that much, but it is emissions from diesel generating or diesel trucks, and so that can cause some air quality issues and certainly quality of life issues, given that a lot of this traffic is also occurring on rural roads. Next slide, please. Okay, so from a chemical engineering perspective, I look at this and I say, wow, this makes no sense, because the energy that would be required to treat the water on site is about 1/10 of the total energy that is expended in managing this produced water. There's a tremendous amount of energy, or energy equivalent, expended in transporting water for transport to centralized waste treatment facilities and transport to injection facilities. There's a lot less energy expended in treating water in a distributed fashion for reuse. You're not removing any of the dissolved solids or salts. You're just basically putting it through a sock filter and reusing it. And then there are some centralized treatment for reuse facilities as well. The takeaway here is that the energy consumed in transport is about an order of magnitude higher than the energy consumed in simply treating that water, using the most using commercially available processes for these estimates. Next slide, please. So we got really interested in why companies chose to treat or chose to transport this water rather than treat this water, and what led to companies choosing to do this. I'm going to introduce just two quick variables. One is average transport distance, which is that 113 miles. We're not going to use that because that does not really characterize a volume transported. Instead, we're going to use something called cumulative waste transport intensity, or some DQ per well. I apologize for the bad variable name. We're actually going to log this. Next slide. One of the things that's really interesting when we look at this is that there is a kind of significant variation in waste transport intensity, both at the well level as well as at the firm level. So we find that some companies manage their waste much more efficiently than others. Some transport their waste much shorter distances than others. Next slide, please. So we worked with a statistician, Brian Junker, at CMU to explain some of this variance in waste transport intensity. And I'm going to go through these quickly, but I want to tell you that the largest effects are ones that have to do with drilling your wells in a spatial temporal cluster, so scheduling effects. And I'm also going to talk about the company experience factor in here. The ones with 2 or 3 stars are statistically significant. You'll note that the ones that are not statistically significant are company size or the location of company headquarters. Next slide, please. So from a scheduling perspective, you can see, and again, this is 2001 data. This is when there was a big change in regulation, so it's an interesting year to look at. We noted that if the well that we were considering the waste from was drilled in a spatial temporal cluster of 30 days and 5 miles, the probability of reuse, and therefore the waste transport distances, dropped dramatically. Next slide, please. The other thing that we noted was that there were some interesting effects with company experience. The total number of unconventional wells that you drilled in the Marcellus had a strong negative effect on the amount of waste transport distance, so it tended to decrease waste transport distance, while the total number of unconventional wells that you drilled nationally did not. And I think one of the reasons that that's interesting is that a lot of the companies that were coming up in 2011, the bigger companies had come in from Texas. And so they had, in this sort of systems planning and process optimization perspective, that the way to handle waste was to do deep well injection. So they did a lot less of the internal recycling than companies that had been drilling in the Marcellus for some years. Next slide, please. Okay, so I want to move on and talk a little bit more briefly about these next 2 areas. The first is sort of optimizing the processes. So since the scheduling component became or stood out as a really important variable in determining waste transport distances and energy intensity of waste transport, we really wanted to look more deeply at what constrains a company's ability to reuse waste. So we've done this kind of top-down analysis, and we wanted to do a bottom-up analysis. We worked very closely with a company based here in Pittsburgh to look at a investment optimization model that considered both freshwater acquisition and wastewater handling, actually in the Utica play, but close enough. Next slide. So this is our case study. We looked at 2 different areas with 14 different pads. Each of those pads had between 8 and 10 wells drilled on it. There are, we assumed the presence of a centralized waste treatment facility that had desalination capacity so that the company could reuse their water even if it was above this salinity threshold that they set of 50,000 ppm TDS. Total dissolved solids. It's a salt concentration. This company wanted very low salt concentrations. I will say that this is not typical of, from my understanding, it's not typical of what many of the other companies are using. Maybe you can elaborate later, but I think that this, there are certainly some service providers that are able to do these frac formulations with concentrations of TDS closer to 200,000 ppm, but this particular company wanted it below 50. So we worked with 50. Next slide, please. I want to point out that the profile of the water being treated changes significantly over time for each of these wells. So you have flow rates that might start out quite high and drop to about a tenth of what they were over a 30-day period, so this is in days. You'll also see that the salinity of this flowback water is increasing just as rapidly. So this is very conceptual, but we had actual data from each well on what the flowback profile looked like and what the salinity profile looked like. One of the things, again, that really complicates the management of all these waters is the fact that there are variable flow rates and variable concentrations of salinity in those flows. Next slide, please. So this is where I do most of my chemical engineering work, is in really looking at advanced water treatment processes for high salinity brine management. I do a lot of work on membrane-based separation technologies, including membrane distillation, which we analyzed in this study, as well as thermal-based technologies such as mechanical vapor recompression, which is a conventional thermal technology that has been deployed on site or in sort of semi-centralized areas. Next slide, please. So integrating those 2 things, the flowback from this series of 14 producing pads, and kind of 3 options for managing the waste. The first is a basic treatment, which is simply removing the dissolved solids through a sock filter, and we did a little bit of divalent caught ion removal in that pretreatment step as well. That allows direct reuse on the completion pad. The second option is to send this to a centralized water treatment facility. We assumed that this was a Suneye mobile desalination facility, and we evaluated a number of different technologies here. We also assumed that the water would either be sent back to this completion pad at a lower concentration of salts, or that it would be discharged to a receiving body of water. This discharge is complicated. Regulatory supervision of that discharge happens on a batch-by-batch basis. There are not, I'm not going to go into it, but I'm happy to answer more about that in the question and answer. The third option is to send this to disposal well. Next slide, please. So we built this mixed integer nonlinear program that took into account, or the objective function of which was to maximize profit. We had a series of allocation constraints as well as material balance and logistic constraints that were given to us by the company. And I'm not going to go through all of these, but I will say that we linearized this MINLP to a mixed integer linear program to ease solving, especially since we were dealing with scheduling constraints, and the problem simply became too big to do in a bilinear way. Next slide, please. And what got spit out at the back end, but is certainly adaptable based on kind of the configuration of the pads and those constraints, is a kind of profile for where water would be optimally sourced from in the drilling of each of these wells. So what we saw was a significant reduction in cost that was largely stemming from a reduction in transporting this water through trucking operations. And I want to clarify, this is not a 35% cost savings in well drilling. This is just in the water management side of the well cost, but still significant. And we also see a significant demand for water desalination. So everything in gray is water that was actually put through desalination facilities in order to meet that flowback or that frac water composition target of 50,000 ppm TDS. Next slide, please. Okay, so our work going forward is really to build optimization programs that are also capable of looking at some of the externalities in this process, both to consider operational costs, capital costs, as well as air emissions in treatment and transport. Next slide. Okay, so how am I doing on time? Okay, cool. That's more time than I thought. I'm doing well. Okay, so I want to kind of wrap up with a study that has not yet come out and is sort of very much a work in progress, but I think might be interesting to this crowd. We kind of got interested in understanding some of the air emission damages associated with this waste transport, not so much because they're all that large, but because they provide one of the few instances of very finely resolved air emission damages or damages from shale gas activity in general within the state of Pennsylvania. So we had this nice data set understanding waste transport distance, and we wanted to understand how the air emission damages associated with that waste transport related to the distribution of impact fees from Pennsylvania Act 13, which is designed to compensate counties for the damages that are incurred during shale gas development. Okay, next slide. So we should talk kind of broadly about damage compensation for shale gas activity, or damage compensation for energy development or any sort of industrial activity in general. One of the things about unconventional natural gas development is that the benefits and the impacts are realized at very different spatial scales. Pennsylvania doesn't actually use most of the gas that's produced, that's used on the East Coast. There are certainly benefits to the region's economy, but a lot of those benefits accrue to the landowner, and the effects on the broader economy, if you have questions about that, you should ask Ken. But I will just say that there has certainly been some jurisdictional conflict over what the appropriate level of regulation is in shale gas, in regulating shale gas activity in the state. So there's been a number of lawsuits that have sought to regain kind of better control over what sorts of activities are allowed at a county level or at a township level. And there's a lot of literature in this area. There's certainly evidence that decentralized regulation can promote economic efficiency by implementing environmental policy that's consistent with local environmental preferences. There's also the possibility that decentralized regulation can lead to underregulation if it ignores the pollution externalities associated with development on a regional level, or excessive regulation when it discounts those net benefits to a region. So what we wanted to look at was PA Act 13. Next slide, please. PA Act 13, about 60% of the revenues collected from PA Act 13 are allocated to individual counties to offset some of these environmental impacts. These fees are paid by companies on a per well basis over a 15-year period, and they're intended both to provide revenue to the state of Pennsylvania, since we don't have a severance tax, as well as to compensate for the damages caused by drilling. As I said, 60% of the funds are allocated for impact mitigation, but what's interesting is that they're allocated in the year in which the well is drilled, they're allocated based on how many wells were drilled in a county in a given year, as well as a couple of other opaque variables, but that's a pretty important one. And as a condition of receiving these Act 13 funds, any county with ordinances that regulate oil and gas operations must allow for the reasonable development of oil and gas resources. So there's some transfer of jurisdictional authority to the state in agreeing to receive these impact fees. Next slide. So what we did is we looked at the annual impact fees and damages associated with wastewater transport. Again, this is a very small sliver of overall damages from shale wells. I just am using this data set because we have really good spatial resolution in a way that we don't have incredibly good spatial resolution or estimates of the emissions from other shale gas operations. So accounting for this wastewater transport, which is about 10% of overall truck traffic and about 50% of overall air emissions, so this ends up being a very small fraction. But we can look at this distribution of impact fees paid to the counties, which again are on the basis of how many wells are drilled. Oops. Ken, you've sabotaged my presentation. Anyway, the point is that this allocation of impact fee and the actual damages experienced from air emissions associated with trucking is really not very well balanced. And this is, next slide please. Of the 67 counties in Pennsylvania, 40 of them experienced negative net damages, even though this is just a very small sliver of the air emissions and damages associated with shale gas development. So the size of the impact fee doesn't actually fully compensate for impacts. That might be okay, given that there are certainly other mechanisms through which the economy is benefiting. But the concern here is that damage compensation schemes that are currently set up in PA Act 13 are also used to dissipate this jurisdictional conflict, and as a result, they tend to disproportionately compensate for local impacts, or the impacts where the wells are actually being drilled, and the counties in which those wells are being drilled. So what we've shown here is that there's an incentive to undervalue these regional damages and therefore set regulations no more efficiently than a pollution exporting local regulator would. So even though we have just kind of statewide jurisdiction, we don't think that the air emission regulations accurately reflect these regional damages. Next slide, please. Okay, so I've gone through kind of emphasizing the importance of system drivers. This looks very different in a state like Texas or in North Dakota, where there are a whole different slew of constraints on both water acquisition and wastewater disposal. We've talked about a generalized method for optimizing water management on shale plays that takes into account both acquisition and disposal. We think that better use of these optimization models in the scheduling and planning of wells especially, so drilling your wells in spatial temporal clusters can be really valuable in both reducing cost and environmental impact associated with water management. And we've talked about some of the difficulties with PA Act 13, and we would suggest that the state revisit that act if they're going to call it an impact fee. Okay, that concludes my presentation. If you can just give me one more slide. Patrick Baer has done a lot of this work. He is now at Harvard, and also, actually this is an old acknowledgement slide, but I really appreciate your attention and happy to answer any questions after we hear from the next speaker.
That should work. All right, make sure it does.
Yep.
Yeah.
Good afternoon, everybody. Well, Megan did a great job of giving an introduction, very nice talk as well. So I'm going to skip some of my introductory slides, or at least go through them rather quickly. But first of all, as I think everybody knows, conventional hydraulic fracturing shown on here on the right, with a vertical interval, has been practiced for probably 50 or more years. But what's worthwhile to point out is that there's a lot of experience in treating the types of fluids that are used, the types of fluids that come back. The main difference is that in the unconventionals, we're talking about volumes that are 100 times greater water volumes. But some of the issues around the fact that these wells could be stranded, for example, offshore, would be considered a stranded location in some sense, and I'll talk about that a little bit more. And the fluids that are used are the same as have been for the last several decades. Again, I'm not going to go through these details, but horizontal drilling, directional drilling, zonal isolation, and so on. These are the technologies that have actually been around for, in some cases, 10 or 20 years. The economics of oil and gas have made them viable, at least until recently. So, comparison between unconventional and conventional hydraulic fracturing. Injection volumes are much greater in the unconventional, and sometimes these volumes can be as high as 400, 500,000 barrels. Injection rates are also much higher. I'll show in a minute what a frac tank looks like, and you'll see that a frac tank will be evacuated in just 5 minutes. Load recovery, that's the amount of water coming back. That varies anywhere from 10% up to 40, 50, or 60%, depending on the water content of the shale. And then the flowback rate is roughly the same in conventional and unconventional. There's a good reason for that. You want to leave the proppant in place, you want to leave the fracture in place, and so that dictates relatively the same flow rate. Just to give a little perspective, worldwide oil production about 80 million barrels per day, about 13 million standard cubic meters. Worldwide produced water is about 3 times that. So worldwide, the ratio of produced water to oil is about 3 to 1. In the U.S., that ratio is about 7 to 1. The U.S. is a more mature oil producing region, so there's a lot of oil. In Oklahoma, for example, that figure is closer to 9 barrels of water for every. Now, water production from the shales, about 8 million. That was a couple years ago during a period of high activity. I don't know what the numbers are now, but you can see that it's a much smaller volume. But still, what makes it significant are the high volumes per well and the cost. Now, when I started my career a long time ago, water was a cost factor. But so this is percent of total cost for drilling and completion, spent by category. With the shales, water suddenly catapulted from the 50th item on the list to anywhere from the range of 3 to maybe 4 or 5 highest, most cost item. And that's created a huge shift in the way the industry looks at water. So that was the background, and so the outline of my talk. What are the challenges of treating water at the well site, production, handling, disposal? How much progress has been made? What have we learned so far, and what can we expect in the future? So this is a very nice summary of what it means to manage water. This is from Steve Tipton at ALL Consultants, and he's kind of outlined the entire challenge. Finding the water, first of all, transporting it, storing it, water treatment and reuse, if that's practiced, and then finally water disposal. This is the early days, one of the things Megan alluded to. Before water became something that you managed and planned, the industry typically relied on frac tanks and trucks. This is a frac tank, 500 barrels, so if you have a hydraulic fracture that requires 100,000 barrels, you're talking about 200 of these tanks. They're usually ganged together in a manifold, and you drain each one of these tanks in 5 minutes. That's volume of water, and that's what we dealt with in the early days. So all those frac tanks and all those trucks give rise to some of the more important items in the risk matrix. So this is a risk matrix. You identify the hazards and then you determine the risks associated with those hazards, and you manage those risks to an acceptable level. The x-axis is the occurrence or frequency that that hazard may be experienced as a hazardous event, and then the y-axis is the severity. And you try to achieve all of your hazards and risks in the lower left. And without going through the details, most of the risks associated with hydraulic fracturing, especially in the early days, was trucking the water, spilling the brine. If you spill oil in oil, there's a chance of biodegradation and a chance of cleanup. You spill a brine, that brine is there for ever, basically, and that will kill any chance of doing agriculture without an expensive cleanup. The initial Marcellus experience, the operators didn't manage water. Transportation costs, rule of thumb that we all use, $1 per barrel per hour. If you're talking about 113 miles per rent, 226 per round trip, you're talking about a significant expense, first of all. And then road traffic accident frequency is very well known. It averages to about 1 crash per 100 wells. A significant number in my opinion. So, in the early days, that created a shift in the mindset toward water within oil and gas companies. No longer an afterthought. And maybe afterthought is the wrong terminology, but water in the oil and gas industry has always been thought of as something that you would plan for and design and handle later, once you know how much water, once you know the water characteristics, and so on. So it's common to build facilities without any water treatment at all. But the shift to planning and management created a huge staffing problem. Where are you going to get all these water treating people who know something about water in the oil and gas industry? And then that has repercussions. It also exposed a long-standing competency problem, and I mean competency in the sense of the competency matrix. They're all smart people, but they don't have experience and competency in water. So this is the first, what I would call, significant development in management of water. And so how did the industry respond? It responded, as it often does, to chemistry, water, fluid-related problems. It tried to engineer those problems. And so the industry developed competency and a supply chain around building lagoons. Some of these lagoons are double-lined with a detection barrier, detection layer in between the two barriers. So the industry got very good at building very large lagoons. It also got very good at designing and building and rapidly manufacturing what we call pelican tanks as well. And this is, in my opinion, I know this is going to sound a little bit jaded perhaps, but in my opinion, this is one of the significant technological developments in the whole hydraulic fracturing water treatment industry, and that's the development of lay-flat hose. Simple, right? This has really changed the way we do business. Pressure rating, significant lengths, and you can take quarter-mile lengths of this stuff that's been connected and so on. You can drag it to a new location. Very reliable. The laydown time is a mile an hour, so 20 miles, 20 hours is fantastic. And then, of course, numerous service providers now in this whole industry. The pumps that go with it, you can pump for 6 miles. This pump right here with a diesel tank, set that out there in the middle of nowhere. And so that has sort of encouraged companies to take a more centralized water treatment approach. But by centralized, I mean centralized storage. It is a little bit hard to see, but this is the South Scoop in middle Oklahoma, a Newfield facility. And you can see all of the well pads, and these are relatively clustered with multiple wells per pad. And then this is just a blow-up of one section. And in this case, what happens is you need water in certain locations, so you go out and you source the water, you put down the hose, you build the lagoon, and in time, the prolific nature of those wells, the productivity and so on becomes proved, Then you realize, well, where do I need to centralize? And then you can start building centralized facilities. And then you can start thinking about water technology to do the recycle and so on. So this development occurred over probably about 4 or 5 years. So the next thing to talk about is, let's talk about technology at the well site. Let's talk about water treatment technology. Water treatment technology discussions should always start with what are the characteristics. High total suspended solids, either polymers that go in, high mineral total dissolved solids, so all the salts that come out of the shale. What are the analogs for these types of fluids? Well, there are lots of analogs. The industry knows how to treat these in centralized facilities. Food and beverage, pulp and paper are excellent analogs for these types of fluids. But the addition in hydraulic fracturing is these fluids will be very variable. In this case, this is oil. In some cases, oil is produced, in other cases not. Very difficult to predict the characteristics. And all water treatment challenges are local and specific, local to the region, local to the well, local to the water sources. So, as I said, we talked about the analogs, but another analog that is often overlooked are all of those conventional wells, conventional hydraulic fracturing. So why is it that we can't use that technology in the onshore unconventional? I'll explain that in a minute. But all this experience points to a couple of technologies that are dominant now and will probably